Okay guys, welcome back. So in the last videos we talked about Kirchhoff's laws and the other concepts in current electricity. So in this video I'll be taking another example of equivalent resistance of a circuit of equivalent resistance, but a special circuit. In which the number of resistors I'll be using is infinity, right? So this will be something like this. So it may be sometimes confusing to you, as I said, like that. So I'll take a simple setup like this, right? Like this, and I'll take the resistance of all these resistors to be of the same value. So this is about finding the equivalent resistance of a circuit in which the number of resistors used is infinite number of resistors. So this will continue up to infinity like this. And I'll take the resistance of each of these resistors to be 2 ohms. To be 2 ohms, here 2 ohms, 2 ohms, 2 ohms, 2 ohms, 2 ohms, 2 ohms, 2 ohms. Like this. And the voltage of the battery I'm using to be take 6 volts, and its internal resistance as 0.8 ohms. So what I'm asking is, what is the current? What is the current that is flowing through the battery? Alright, so what actually happens is, now this is a case actually. Now if you want to find the current, we have to find the equivalent resistance and then find. So that's the easiest way without going through Kirchhoff's laws, because if you are using infinite number of loops, now this is one loop, second loop, third loop, so like that infinite number of loops, you have to put these Kirchhoff's laws into infinite number of loops, right? So that is completely out of question, because actually that is completely useless, and you don't need to do that, right? So what actually happens is the other way. The other way is that if you can take the equivalent resistance of this circuit, you can again find the current that is flowing through this cell, because the voltage and the internal resistance is given. Alright. So how are we going to find the equivalent resistance of an infinite number of resistors, or infinite loops of resistors? Alright, what actually happens, now you see what actually happens if I break the whole circuit from here. If I break the whole circuit from here, like this. If I break it like that, what actually happens is that now this part is analogous to this part, right? And this part, if I break it from here, is analogous. This part is analogous to this one. This is like just copy pasting, right? You take some image, you copy it, you keep on pasting, and then finally you join it, or you merge it. So this is like simply like that. What actually happens is that this is the same part that will be recurring throughout until it goes to infinity. So I'll take the total resistance of this whole set, from the first set to that in the infinity to be R, and I'll connect that here, right? Because this is the same set that will be recurring. So this will simplify now to this setup. So here will be 2 ohms, right? 2 ohms, and this resistance is also now 2 ohms. This resistance also now 2 ohms, and the total resistance of the loops that I will be changing, I will be substituting, or I will be representing, right? Representing will I take as capital R. Capital R, because this is the same set that will be recurring throughout. So the voltage of this will be 6 volts, and internal resistance 0.8 ohms, right? 0.8 ohms. So what is the equivalent resistance? What is the equivalent resistance of this circuit? Alright, now you see that what actually happens is that the equivalent resistance, the equivalent resistance of this circuit is, you can put now these two what you call resistors. These two resistors are in parallel, so you can take the equal resistance of that. So that will be 1 upon R EFF1 is equal to 1 upon R plus 1 upon 2. So that will be R plus 2 divided by 2R. So that is 1 upon R EFF1. So R EFF1 is equal to 2R divided by R plus 2. So now if I connect this, it will be like this. So this will be 2 ohms. This will be 2R divided by R plus 2. And this will be 2 ohms again. And the voltage will be the cell. And this will be 6 volts and this will be 0.8 ohms. So the whole setup of infinite number of loops will simplify to this portion, right? To this portion. So what actually happens is that alright. So we can now, if I pass the current I from here and if the current I comes here, what actually happens is that now the same current passes through all these points, but these points are not at a single voltage point, right? A single voltage point, right? These do not know the voltage at this point and this point is not equal to the voltage of this point and this point due to these two resistors. So these are actually in series, not in parallel, because the same current is flowing, but the voltages of the individual resistors are different. Right? So what actually happens is that now these are in series means now that we can take the total effective resistance, the final effective resistance REFF as 2 plus 2 plus REFF1, which is 2R divided by R plus 2, right? 2R divided by R plus 2. So that will be 4 plus 2R divided by R plus 2. So this will be 4R plus 2R, which is 6R plus 8 divided by R plus 2. 6R plus 8 divided by R plus 2. So that will be the total effective resistance, right? Now what actually happens is that we can put, now this is very simple to this one, we can further simplify this to this one. This. So that this is 6R plus 8. So R has been given as 2, right? So R is equal to 2. So the resistance is 2. R effective will be 6 times 2, which is 12. 12 plus 8 is 20. Divided by 2 plus 2, which is 4. So this will be 5 ohms. So this will be 5 ohms. And here will be 0.8 ohms. And will be 6 volts. So we have to find the current. Right? We have to find the current. Right? We can simplify like this. So we found the R effective to be 5 ohms, substituting R equals 2. So we can put the current notation. You don't have to actually know. These also equal, these also the same as the Kirchhoff's laws, but this you can put the current notation easily. So what actually happens is that 6 is equal to 0.8I, which is the voltage across this cell, right? 0.8I, right? Plus 5I. So 6 will be equal to 5.8I. So I will be equal to 6 by 5.8. That will be, I think, approximately equal to 1, right? 1 ampere. Approximately equal to 1 ampere. Alright, so approximately a 1 ampere current flows through a circuit when you connect such a circuit into infinite number of resistors like this. Excuse me. So what actually happens in this circuit is that we can equally take this to be the same thing, right? This to be, now this part to be the same thing as this part, like this, right? Same thing, and that is also the same thing as this one. So what actually happens is that the same thing is recurring again and again. So we can tell that this is actually equal to this R. We found R to be 2, and we found finally the I to be approximately 1 ampere. So what actually happens is that you can find the resistance like that. So there is another topic which is a thing you can find from Kirchhoff's law, but will be very tireless, and in my preference I think it is useless because it's very time consuming, and it will be sometimes inaccurate if you solve too many equations, right? So it's the best way is to find the equivalent resistance and then find the final current, right? So that's another example in which both the Kirchhoff's laws, the current notation, and the equivalent resistance come into play together, and that's a new concept. And hope you enjoy this video and get some information from it. And thanks for watching this video, and see you next time with another concept in current electricity.